Hello, my name is Juhan Park. Today I will introduce 3D MEM, 3D Scene Memory for Embodied Exploration and Reasoning, a paper accepted to CVPR 2025. Embodied exploration and reasoning refers to tasking an agent to interact with an environment or a scene through movement and sensory input. The agent explores the scene to gather information, which can then be used for tasks such as answering questions, solving problems, and building a structured understanding of the scene. Enabling the agent to understand the scene requires the agent to be equipped with crucial abilities, including the memory system for the scene. For example, if the agent was asked about the color of the sofa in the living room, it must recall the scene memory to answer as, "The sofa in the living room is white." This implies that there is a need for a means of representation for 3D scenes that can be used to store into memory database. The most commonly used approaches for 3D scene representation are dense 3D representations and scene graphs. Dense 3D representations preserve spatial information with minimal loss, making them highly accurate. However, they are computationally expensive, and vision language models, widely used for agent reasoning, cannot directly process raw 3D data. Scene graphs, in contrast, offer real-time construction and support dynamic scene updates. Yet, they often oversimplify inter-object relationships and depend heavily on predefined relational schemas, limiting their expressiveness and adaptability. Today's paper, 3D MEM, presents a novel 3D scene memory framework designed for vision language model-based agents. Instead of dense 3D representations and scene graphs, they leverage multi-view images to store the scene information. Built on this framework, the authors implement an embodied exploration and reasoning task. When presented with a question, the agent first consults its memory. If the stored information is sufficient, it answers the question. Otherwise, it further explores the scene to acquire the necessary data. Now we examine how the memory system is implemented. The authors make an assumption that an image itself inherently contains rich and robust information to represent the small area of a scene depicted in the image. A set of multi-view images would then be sufficient to cover the whole informative areas of the scene. Based on this assumption, the memory snapshot mechanism is introduced, which stores information from previously visited areas using these multi-view images. Each memory snapshot consists of two components, the image itself and a corresponding cluster of objects detected within it. Such approach allows the encapsulation of not only the object-level local details, but also the contextual room-level cues embedded in the background. However, it would be computationally inefficient to store all multi-view images, especially when many contain redundant information. To address this, the memory snapshot system aims to reduce the number of stored images by identifying a minimal subset that still covers all relevant objects. For example, suppose an agent visits our living room and captures 3 images. The first includes a sofa, coffee table, and rug. The second includes a TV, clock, coffee table, and rug. And the third includes sofa, coffee table, and TV. In this case, the third image is redundant as its object content is already represented in the first and second. The memory snapshot mechanism is designed to perform this kind of selection, retaining only the essential images needed to cover all observed objects. When the agent captures multi-view images, they are processed using the method introduced in the concept graph paper, which detects objects and estimates their 3D coordinates to construct a global object list O. Each entry in this list contains 3 components: the object's category name, the detection confidence score from the segmentation model, and the predicted 3D coordinates. For instance, The first entry in the list might represent a sofa with a confidence score of 0.96 and a 3D location of 357. Using the global object list, we then construct frame candidates, each consisting of an image paired with a set of detected objects present in that image. Although these frames serve as candidates for memory snapshots, redundant ones must be removed first. To achieve this, the authors propose an algorithm called co-visibility clustering, which identifies and eliminates overlapping frame candidates. Rather than diving into theory, I'll walk you through a simple example to illustrate how the process works. We begin with a single object cluster that contains all detected objects in the scene. Next, we check whether any frame candidate contains all the objects in this cluster. We see that no such frame exists in the current step. We now proceed to divide the object cluster. The cluster is split into two using the k-means algorithm, which groups objects based on the distance between their 3D coordinates. Suppose the sofa, coffee table, and rug are spatially close and form one cluster, while the TV and clock form another. We then compare the first cluster against the frames. This time, frame 0 is found to contain all objects in the first cluster. We pair object cluster 1 with frame 0 to form a memory snapshot 0. Next, we evaluate the second cluster against the remaining frames. Frame 2 is found to satisfy the condition. So it is paired with object cluster 2 to form a memory snapshot 1. Since all objects are now covered by the selected frames, the remaining frames 3 is discarded. This is a finalized set of memory snapshots that efficiently covers all detected objects with minimal redundancy. The frontier snapshot is rather simple as it records the image of the entrance to the area that is yet explored by the agent. Now that we've examined how the memory system works, let's explore how it gets updated as the agent navigates through the new areas. When the agent encounters new observations, it captures multi-view images and detects objects within them. These detected objects may be entirely new or previously observed. The system then compares the newly detected objects with those stored in existing memory snapshots. If there is no overlap between a memory snapshot and the detected objects, the memory snapshots remain untouched, such as the colored ones right here. However, if our overlapping objects are found, the corresponding memory snapshots are marked for reclustering along with the newly captured frames, as with these gray-colored clusters. The selected snapshots and new frames are then passed through the co-visibility clustering algorithm, again to reassign memory snapshots. In this process, previously stored snapshots may be discarded if they become redundant. While co-visibility clustering reduces redundancy, the memory inevitably grows as the agent continuously explores the scene. To address the challenge of querying an increasingly large database, the authors introduce a pre-filtering method. This approach allows the vision language model to first select a subset of relevant frames based on the query, thereby narrowing down the number of memory snapshots the VLM needs to examine. The authors evaluate their method across 3 experiments. The first focuses on question answering using the AEQA dataset. They compare their approach against several baseline agents: blind LLMs, which operate without visual input; question-agnostic exploration, where the agent explores the environment without knowledge of the upcoming question; and VLM-based exploration, where the agent uses a vision language model to guide its exploration based on the given question. Evaluation is based on two metrics: LLM match, which uses a language model to assess the correctness of the agent answers, and LLM match SPL, which extends this by also factoring in the efficiency of exploration, penalizing agents that take longer to find correct answers. The evaluation results show that 3D-MEM outscores the baseline for both the LLM match and the LLM match SPL. The second experiment is episodic memory embodied question answering, which evaluates the effectiveness of image-based scene representations compared to text-based descriptions. The authors used the EMEQA dataset for evaluation, with baselines including language-only scene representations and multi-frames, which utilizes raw multi-view images without further processing. The results demonstrate that 3D-MEM outperforms all baselines. As shown in the figure on the right, 3D-MEM achieves higher accuracy scores using the same number of frames as multi-frames, highlighting its efficiency in memory utilization. Although the paper introduces an efficient scene memory framework, it comes with several limitations. First, it is limited to static environments and cannot handle scenes with moving objects. Second, the method's effectiveness is tightly coupled with the performance of object detection models and VLM-based reasoning. Third, it assumes access to the agent's precise location, which may not always be feasible in real-world scenarios. Finally, the system exhibits noticeable latency, taking up to 7 to 8 seconds to complete a single question answering task. Thank you.